Hello everyone, welcome to another Dr. Sarkis video, and first of all I should like to introduce you to this new setup here. Now I'm hoping that it's more comfortable for you because my previous setup was appalling, and yeah, I just wanted to say sorry for that. Also, my first video is about Laplace transform, that was in portrait mode. I don't know why, like clearly it has to be landscape, but okay, so I hope that this video you should get along with it better, because it's clearer and the angle is better, such that you can see the whole page without me having to move it all the time. Okay, so we've shown that you can use rectangles in order to approximate the area under the curve, and that is done by having infinitely small or infinitesimally small width rectangles, and that's a very simple way of thinking about it. But surely, with all the gaps you have here, because now I'm just comparing between the two models, and with the rectangle model, you see those gaps here, and they're not good, because where we have a gap, then that means that your approximation isn't taken to its full potential. So actually, I will show you that in fact there's an even better way to approximate the area under the curve in the Trapezium Rule. That is called the Simpson Rule, but that's for another video, so we're just going to tune in and focus on this particular method. So let's crack on with it. So from secondary school, you probably know that the area of a trapezium is h over 2, with h being the height of that trapezium, with of a plus b, and actually here yn acts as a, and yn plus 1 it acts as b. So this is just us kind of representing this formula over here, which is very widely known. I mean, and what we have here essentially, this really long formula, whether this just means approximates. So essentially what we have here is we have a kind of rearranged form, because in order to add all the trapezia we have here, which can become quite tedious, well, that just takes a lot of effort. So mathematicians have looked at it and said, you know what, the first points in a given function, in a given integral, so a, but also b, the last point as well, they only really pop up once in this computation, as you see. That's only one time they appear. Everything else in the middle is times by 2, and the reason of that is it's just a shortcut, a way of calculating the trapezia. You just kind of rearrange it to get this easier form, because the idea of calculating all the trapezia separately and then adding up, it becomes really inefficient. So mathematicians have just rearranged it that way to make it more intuitive. And then it's useful to know that in a question they will tell you use n amount of strips in order to show an approximation of the area under the curve, blah blah blah. It's useful to know that we can use this formula to kind of find that needed height for the trapezia we're gonna create. So I'm going to give you an example. Regardless of this, ignore this. This is just a basic drawing. It's nothing to do with the function I have here. This is an exponential function and it goes like that. Definitely not like the sinusoidal curve we have here. So what's x of 0? What's the original point here in this question? We are asked to use 6 strips And by the way, this is overkill. I don't think you'll get any question with 6 strips, but I thought it would do you good to get used to having intrinsically harder questions, so that by the time we get to the actual thing, you'll be like, oh, that's easy. Okay, so we have this integral over here. It just means the integral of the area under the curve of e to the power of x from a point x equals 1 to x equals 4. And so what we do is, the first point over here is just going to be 1. We know that, because that's the first bound. So we insert that, and the second point is going to be, 4, not 1. And then in order to find this optimal, or not optimal, the necessary width or height here, in the case of trapezium, that's just the way it's called. What we do is, we substitute the values, so b minus a, so that's 4 minus 1, divided by how many strips you are meant to use. So we have 3 divided by 6 equals half. Great. That's very easy to remember. Okay. So we just gradually increase the previous values. We increment by that value 0.5, which is our preferred width. Just to make it clear, I'm not rounding anything here. This is completely the numbers you can see here. They are what it is. I don't know. I'm probably quite tired if I'm making that kind of mistake. Where did I go wrong? Just trying to think for a second. Yeah, that's a bit odd. Okay. Sorry for that. We don't really need this. Yeah. So we just have this table. Okay. Okay. So then what we're going to do now is we're going to just compute with values and then substitute that into the lovely equation we have here. So I'm just making sure that you can see. I'm not sure you can see. What's e to the power of 1? What do we have here? And that's the corresponding function which we're meant to. That's e. Of course, I don't need the calculator to show that. Okay. And then what about e to the 1.5? I'm just gonna, okay. First, just gonna write it out fully. I used to know 100 digits of pi and like 20 digits of e, but at some point I said to myself, you know what, it's not really important, so may as well just stop. Right, and then e squared. Sounds weird, e squared. And then e cubed. Not quite there. Back to the next one. See, I'm really tired. I've been waiting for this camera stand for like 2 hours, and then it came, and I had to set it up. And now it's like 1 AM, and I'm really exhausted. But just for you guys, for the sake of mathematics, I decided I want to undertake this adventure with a new camera stand. So hopefully you can see what I'm doing. it's not really worth it if you can't see what I'm doing. But I'm just working out the values for y here, for each point. Okay, so now we can substitute. Woohoo! That's great. What we do now is we do the height, so which we've shown that it's actually just 0.5. So 0.5 divided by 2. All of that times our first value here. I'm just going to write e to make things short. Plus 2 times 4.4. Yeah, I'm just going to write this thing out. Plus, yeah, you can get the idea. Just going to quickly write everything here. Yeah, hopefully by now you would have noticed that my handwriting is absolutely atrocious. And then we have our last point. So the last point is outside of those brackets. It doesn't deserve a pair because it's in the last. It's the last bound. It's B. So we give B and A solo in this rule. Yeah, that is 0. I can't read my own handwriting at times, which is a bit funny. Okay, so let's just calculate this. I don't know if you probably can't see. But it's just a calculator, there's nothing interesting about it. Okay. Actually, it would probably save time if I just calculated using the e to the power of n kind of system here. Okay, here we go. What is the answer? The answer is, it is 52 minus 9, not 52, 0.95622,197. That is roughly equal to 52.96 for significant figures, just like we were asked to do. So that's it for today, and that is a really long video considering that it's a really dead easy topic. So yeah, I hope it wasn't too boring, and I hope it wasn't too challenging as well, because I know I tend to go off and become really associative with my explanations. But yeah, if you can subscribe to my channel or like my videos, share it with your friends. If this is an exponential function, right now I'm at this point in the beginning when it looks like the function is not making any progress. So if you could kind of catalyze this point, by which I have a fair amount of subscribers who support the content, then I suppose I'll have more time and I'll have more. I have the tools to produce more useful content than this. So yeah, we'll see you in the next video.